We've seen one example to where we've taken a um, basic system where x was equal to r cos theta, y was equal to r sine theta, and we translated that and we made a Jacobian. So let's take a look at a different region. This time it's more linear, and we're going to take something that's a little more difficult and translate it into something easier to work with. So suppose we have this region R, all right, and R is bound by 4 lines. And the 4 lines are x plus y equals 1, x plus y equals 4, x minus 2y equals negative 4, and x minus 2y is 0. Let's suppose for some reason we wanted to use a double integral to evaluate, or we wanted to evaluate a double integral over that region. Well, unfortunately, if we were to do that using a type 1 integral, we'd actually end up getting 3 double integrals to be able to evaluate this, okay? Hardly efficient. Even if we were to use it as a type 2 integral, we'd probably end up with 3 different regions as well. All right, so that would be much more difficult than necessary. If we were to translate this into a purely rectangular region, we might have a shot of being able to evaluate this a little bit nicer. So let's do this. Let's take x and y and let's use a transformation. I'm going to define u as x plus y. I'm going to define v as x minus 2y. And now what we have is we basically have a system of equations. And what we can do is we can solve for x and we can solve for y, and then we can try to be able to get a transformation. Right? So what I'm going to do is I'm going to multiply u by 2. So 2u is going to be equal to 2x plus 2y. And we have the relationship that v is equal to x minus 2y. And we can add those together. If we add them together, we get 2u plus v is equal to 3x. And then we can divide everything by 3. So we can solve for x readily and say that 2/3 u plus 1/3 v is equal to x. This is a transformation of x from one variable into 2 variables. Okay, so that's like our function. We can call that g of uv. Now to solve for y, we can do that very easily because remember we had this relationship that u equals x plus y. We could just back substitute and solve for y very easily. So we know that u minus x is equal to y. We're going to substitute for u, or for x, excuse me. So we know that u minus what we just got, which was 2/3 u plus 1/3 v, and that's going to be equal to y. And then finally, we just subtract. So we ultimately end up with the transformation for y. That y is going to be equal to 1/3 u minus 1/3 v. All right, we're going to hold on to those. That's our transformation t. If we couple those together, we can translate from xy into uv. So now what we have is we can say that xy is equal to a transformation in uv, and the transformation is going to be exactly those two equations that we just found. So that's going to be 2/3 u plus 1/3 v is our first coordinate, because that's x. And then finally, we have the 1/3 u minus 1/3 v. And that's our transformation. Right? Now, the question is, does this really help us? All right, and in fact, it's going to. What's going to be helpful for us is to both look at it algebraically and geometrically. All right, so let's take a look at this algebraically first. So first of all, we have the xy plane. And in the xy plane, remember we had that u was equal to x plus y. Or, I'm sorry, we had, and we did have that. But in the xy plane, we had x plus y equals 1. We had x plus y was equal to 4. And I'm getting these all the way back up top. from this original graph. Okay, so we have x plus y equals 1. We have x plus y equals 4. We have x minus 2y is negative 4. And we have x minus 2y is 0. When we hit it with the transformation t, we translated that into the UV plane. And in the UV plane, remember we said that u was equal to x plus y. So x plus y is u, so u equals 1. Then we have u equals 4. Remember v was equal to x minus 2y, so v is negative 4, and v is 0. To kind of get an idea of what this looks like geometrically. Remember we had this is with the original region, so I'm just going to paste that underneath here. And what does it look like geometrically now? Well, we hope it's more simplistic than the region we started with. Now remember, u is basically, these are now on a set of axes. Okay, so this is the u-axis, the horizontal, and the v-axis is the vertical. The line u equals 1, that's going to be where u is always equal to 1, so that's going to be a vertical line passing through 1. So let's just call that the first axis, u equals 1. And then let's call this the region, or the line, u equals 4. v equals negative 4 is going to be a horizontal line passing through negative 4 all the time. And then finally, v equals 0 is going to be another horizontal line. All right, mine's not so horizontal, but it's close enough. I'll try to erase it. Let's try it again. So we get a horizontal, a little bit better. And notice what we did was we hit that region that was almost a diamond, and we hit it with a transformation. And now it's a much easier region to work with. In fact, it could be either a type 1 or a type 2 integral, and it could just be at our mercy as to whether we want it to be either type 1 or type 2. And not only that, it would only take a single double integral to evaluate the region. We could even see the mapping if we chose to by substituting the coordinates of UV. So if we wanted to go back, that would almost be like an inverse transformation. All right. Now we have these points. So we have the point 1, negative 4, and we have another point 4, negative 4. We have a third point 4, 0. And then we have a fourth point, we're going to call that 1, 0. And some of these points map, or one point, there's a one-to-one correspondence between the XY plane, let's call that R, is going to be the first region, and let's just call this region Q. All right? It's the same area, all right? It's just going to be a different it's just transformed, all right? And then the question is, how do we map Q into R? Okay, well, remember we have the mapping. Remember we have that XY was equal to T of UV, and remember we had a relationship between the two. Okay, so I think we had 2/3 U plus 1/3 V. And then we had 1/3 U minus 1/3 V. And this is a mapping. And we can illustrate that very easily to see which points in region Q map to the region R. So let me show you an example. Let's say for some reason I wanted to find, let's just pick one at random, let's say 4, 0. So T at 4, 0, and let's see what that equals to. So that would be 2/3 of 4 plus 1/3 of 0, and then it will be 1/3 of 4 minus 1/3 of 0. Or, in other words, T of 4, 0 is equal to a point xy. Remember, it's equal to a point xy, which is going to be equal to the point 8/3, comma, 4/3. And that's a mapping. So if we go back up here, take a look at this. This point 40 maps exactly to the point 8/3, 4/3, which is going to be this point right here. And we could do this for all 4 of the points if we wanted to see what the correspondence is. All right, so I'll just do one more example. I'll just do 1, 0 for simplicity. Okay, so if I wanted to see what the correspondence was, let's find t of 1, 0, and that would be 2/3 times 1 plus 1/3 times 0, comma, 1/3 times 1 minus 1/3 times 0. And that would just give us the point 2/3, 1/3 and xy. So that's going to be equal to a point xy, which is equal to 2/3, 1/3. And so there should be another point on the original region R, and that's our mapping Q, that should be able to map those. Okay, so if we go back up here, we do indeed have the point 2/3, 1/3. And that maps to this point. In fact, what I'll do is, let me undo that, use a different color just to illustrate. So this point that we have, this 2/3, 1/3, maps to this point 1, 0. And so we could do that with the other ones if we chose to. So that's our transformation at this point. Now in the next video, what we're going to see is how do we take all of this and how do we evaluate a double integral for that region R. Okay, so go back, make sure you understand the transformation of this, and then we can go ahead and try to figure out what the double integral might be.